Numericals on Young's double slit experiment. Some formula used for a bright fringe. Path difference is given by P equal to n lambda, where n is 1, 2, 3, 4. For a dark fringe, P is given by 2n minus 1 lambda by 2, where n is 1, 2, 3, etc. Now, distance of nth bright fringe from center of the screen is given by xn equal to n times d lambda upon small d, where n can be 1, 2, 3, etc. And next point is distance of nth dark fringe from center of the screen is given by xn dash equals, it will become 2n minus 1 odd multiple 2n minus 1 d lambda upon 2d. Now, fringe width beta is given by lambda capital D upon small d. Angular position of nth bright fringe is given by theta n, which will be equal to xn upon d. So from here, d will be divided. So n lambda divided by d will be left. Angular position of nth dark fringe, theta n dash, will be equal to xn dash divided by capital D, and that will be equal to 2n minus 1 times lambda divided by 2d. Now let's do some numericals. In Young's double slit experiment, the two parallel slits are made 1 millimeter apart and the screen is placed 1 meter away. What is the fringe separation when a monochromatic radiation of wavelength 500 nanometer is used? So we write the information. Small d is 1 millimeter. So 1 into 10 to the power minus 3 meter. And this is capital D is 1 meter. Situation looks like this. This separation, this is S1, this is S2, and this is D, and this is screen. So this distance is capital D. And wavelength of light uses 500 nanometer, means 10 to the power minus 9 meter. Now we have to find out fringe separation, that is fringe width. Fringe width beta is given by lambda d upon small d. If we put the values, we will get 5 into 10 to the power minus 4 meter. Valuation is left to you. Next question. Laser light of wavelength 630 nanometer. Here, lambda equal to 630 nanometer. Incident on a pair of slits produces an interference pattern in which the bright fringes are separated by 8.1 nanometer. Sorry, not nanometer, millimeter. So here, beta 1 is given as 8.1 millimeter. So let's write this wavelength as lambda 1 because two wavelengths are given and two fringe widths are also given. Now here, a second light produces an interference pattern in which the fringes are separated by 7.2 millimeters. So beta 2 is given as 7.2 millimeter. And find the wavelength of second light, means lambda 2 is to be found. So we know that beta is given by lambda d upon small d. Here, slit width will be constant in the two cases, and value of beta 1, beta 2 are given. So if we find the ratio of beta 1 to beta 2, so here it will be lambda 1d, d is fixed, and divided by small d is also fixed. Divide by beta 2. So beta 2 will be equal to lambda 2 d divided by small. So beta 1 upon beta 2 will be equal to lambda 1 upon lambda 2. And our concern is to get lambda 2. So that can be easily done because values of beta 1 and beta 2 are given. And answer will be 560 nanometer. So you have to evaluate. Next one. Yellow light of wavelength 600 angstrom produces fringes of width 0.8 millimeter in Young's double slit experiment. What will be the fringe width if the light source is replaced by another monochromatic source of wavelength 7500 angstrom and the separation between the slits is doubled? So in this case, we are given lambda 1 equal to 6000 angstrom and beta 1 is given as 0.8 millimeter and lambda 2 is given as 7500 angstrom. Now we have to find out beta 2. The situation is for first one, beta 1 equal to lambda d upon small d. In case of beta 2, condition is changed, wavelength is changed. So suppose this is lambda 1, so this will be a lambda 2. And here, if light source is replaced by another one source of light wavelength this much, and separation between the slits is doubled. Capital D remaining same, small d becomes twice. So this is the condition. Now by using this condition, you have to find out the value of beta 2 and that is very simple. If you write beta 2 upon beta 1, so it will be lambda 2 d divided by 2d times lambda 1 d divided by d and simplify and then put the values and the answer will be 0.5 millimeter. So beta 2 will be equal to 0.5 mm. Now let's go to next question. Question number 3. In Young's double slit experiment, fringes are obtained on a screen placed at certain distance away from the slits. Here separation means this distance is suppose d. If the screen is moved by 5 cm towards the slit, next time situation is changed, the screen is moved toward the slits. These are slits S1 and S2, S1, S2. So this time D comes here. So we can say new D or D dash will be equal to D minus 5 centimeter as per the question. So here, if the screen is moved by 5 centimeter towards the slit, then the change in fringe width is 30 micrometer. So change in fringe width is given. Now, if the distance between the slits is 1 millimeter, means separation between the slits small d is given as 1 millimeter, then calculate the wavelength of the light used. So let's see how. So now beta is given by lambda capital D upon small d. And here rest things remain same. So beta dash equal to d dash times lambda upon d. Only the separation is changed, wavelength remains same, and beta dash are given. So difference in the two, beta minus beta dash, will be equal to lambda d upon small d minus d dash lambda upon small d. So it will be d minus d dash times lambda upon small d. So our purpose is to get lambda. So we can write it like beta minus beta dash times small d upon capital D minus d dash will be equal to lambda. Now we are given capital D minus d dash will be 5 centimeters. So we can say d minus d dash is 5 cm. That can be written as 5 into 10 power minus 2 meter. And difference in fringes is 30 micrometer. It means beta minus beta dash is given, that is 30 micro means 10 power minus 6 meter. So we have got beta minus beta dash, d minus d dash, and also separation between the slits is given, means small d is given as 1 millimeter. So 1 millimeter means 1 into 10 power minus 3 meter. So we can put these values and then we will get lambda as 600 nanometer. Let's see next question. Question number 5. It's not 6. So question number 5. In Young's double slit experiment, the fringe width is found to be 2 millimeter. Means beta is given as 2 millimeter, and wavelength of light used is 6,000 angstrom. Calculate the fringe width if the whole apparatus is immersed in the liquid. Means mu is given as 1.33, and we have to find out beta dash. So let's write it. We know beta equal to lambda d divided by small d, and beta dash when immersed in a liquid of refractive index mu, it becomes beta divided by mu, that is 1 upon mu times lambda d upon small d. And here lambda d upon small d is fringe width itself, so that is 2 millimeter. So 1 upon mu, mu is 1.33, and this is given as 2 millimeter. So if we divide 2 by 1.33, so we will get 1.5 millimeter, which is our answer. Thank you for watching.